I have to sing you a song?
Are you going to? You should.
I wasn't planning on it. What song do you want? Okay, I don't know it.
Twinkle, twinkle, little star.
How about Jesus loves me, this I know, for the Bible tells me so.
Watch this gonna look at the recording.
Are you recording? Oh. On to the lesson. Okay, so we talked a little bit about the harmonics and all that good stuff. And do you do this when you tune?
No, she's my phone.
Oh, that's true. Keep forgetting that's an option now.
Plus, it's like quicker. It's way quicker to do it with the phone.
It might be.
I know it's like
You can do this without having to pull out your phone.
Yeah.
So it's those two, and you just hit over the metal part, the fret, and you'll get that. Now, what I want you guys to listen to is beats. That's what we're going to try to cover 3 concepts today. Oh, by the way, my strategy at this point is that we're going to actually finish the lab maybe starting Friday or next week. All right. So we're going to focus on getting ready for the test.
Maybe like lab period, okay?
Yeah, we'll see, but we're not going to do it this week.
Wait, does that mean we'll have 2 labs on Monday?
No.
Don't worry about it.
Would you do that to us?
Dude, no, just don't make him think about it.
Like last week we had 3 labs in a row. Last week we had 3 labs, so we could do it.
And I might do it to you again.
You shouldn't though.
Yeah. Okay. So just get ready to suffer. So beats. What are beats? Those of you guys that do some music, you know when something isn't in tune. How do you tell when it's getting close to being in tune?
Slow.
Slower. Yes. What waves are we talking about? And
Wow, wow,
the wow wow. And the wow wow
wow. Okay.
is what we call beats. Okay, so Alex, let it rest for a little bit. Beats. And the beats are, you remember the wave edition assignment I gave you?
Huh?
The wave edition where you had to add the waves on paper and so forth. That was Q's favorite one. The last one. What comes to your mind when you did that last one?
Pain.
Pain? Okay. What did it look like?
Accordion.
So did it go from smaller to bigger to smaller again?
Yes.
The height of the waves, right? So when they add together, they're going to be constructive interference. The intensity, the loudness is going to get bigger. When they are actually out of phase, they will destructively interfere and cancel out and be nothing. And this is what creates the wow, wow, wow. Because you get the wow, that's the louder part, and then it goes quieter as they destructively interfere. So I want you to hear it. I'm going to try to do it on the guitar. And right now, they're in phase. There's no wow, wow, wow. All right? So here we go. All right. So I want you to raise your hand as you think it's getting into, that it is in tune. So keep it down if you think it's not in tune. And as it's getting closer, you tell me, yeah, I'm getting closer, 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 all right? So you tell me when we're in tune. All right, put your hand out. This is going to mean that it's out of tune. Okay, here we go. Whoops. Yeah, we're in tune. Yep. He's lost his hearing since he did that last lab. All right. What are you listening for? How do you tell whether or not something's in tune? Well, it's running out of energy, so it's getting quieter no matter what. But it's the wow wow, right? We want to get those beats. The slower the beats, the more it's in tune. And the more you can learn to listen for that, the better musician you're going to be. Let's try it again. right, we're gonna try it a different way. I want you to put your hand out kind of in the middle, and you're gonna tell me we're going too far this way or too far this way. And you're gonna be that digital phone tuner, all right? You help me know when I'm in tune. Here we go. All right, good. You guys are doing good. Do you hear the beats? Okay, the next question is, what is the frequency of each string? Let's say that one string is 100 and you have 5 beats. What's the frequency of the other string? One string is 100 and you have 5 beats. What's the other string? 500? 1,000. Why did you choose 500?
Because the ones we're gonna have it there hitting 5 times, so it's very interacting with each other.
Okay.
It's a lot of like faster.
You guys remember when we did the strobe light back there? When we had it the same flashing as the string was getting the frequency, it made the string look like it was sitting still, right? How much did we have to change it to get it to where it didn't look like it was sitting still and it started to move? Just a tiny bit, right? It doesn't take very much. In essence, we are creating beats in the same way. So if the one string is 100 and we have 5 beats, the other string could be 95 or it could be 105. I don't know which one. Maybe your ear can tell, but otherwise you don't know which one it is. If you know there's 5 beats, you just know the difference between their frequency is what? 5. All right, there's another way to think about it. Let's say that you and your boyfriend or girlfriend are walking, and it's entirely possible that you're not the same height. Therefore, you don't take steps that are the same size, right? So you start walking, and when you start walking, you're in phase or you're in step. Kind of like marching, left, left, you start out, right? But since her step is smaller than his step, possibly, eventually you're out of step, right? How many steps, let's say that he takes 10 steps, and when they're back in phase, when they start, it takes 10 steps for him to be back in phase with her. How many steps did she take?
Like
11. 11. Why 11?
Wait, say it again?
If he takes 10 steps, and her steps are shorter, so they start walking together in phase, but then they're out of phase. When they finally get back in phase again, how many steps will she have taken?
Is it 11?
Like,
Because
how
10
much
would have been
am I supposed to
in phase for him.
It's just one more step than he did, because when if they're back in phase, she's going to have to do one more step than he does to be back in phase.
Because she's shorter.
Because she's shorter.
Why is it only 11?
Because if it was 12, she would have passed him.
Because she's only one step behind him. So for him to get to 10
Is
phases.
this testable? Or is this like
It is testable. This is a little bit different, but it's testable. It's just hard to get you guys to walk consistent. You want to try it? No? Okay. I don't know how else to illustrate it. That drawing that you guys had to do in, I'm going to try to draw it. I don't know if I'm going to make it. I'm going to try it. I'm going to try it. That was the easy part. Now, let's see if I can. Okay, so here we are in phase, right? We're not in phase again until we are here. We're back doing the same thing at the same time, right? So how many waves, how many crests do we have? 1, 2, 3, 4, 5. And how many do we have here? 1, 2, 3, 4, 5, 6. So every time we get back in phase, one will have gone one more than the other one.
And no more than one, no less than one. It's just always one.
It's always one. Now, when we hear the wow, 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 the next question we have is how many wows did we get in a second? How many wows did we get in a second? So if this takes 1 second for this to happen, how many wows would we get? 1. If it takes 1 second for this to happen. What if it takes 5 seconds for this to happen? I should say it takes 5 of these can happen in a second. How many wows would you get?
5.
5. Okay. Per second.
Because to make a wow, it has to go up and down and come back. So if it's doing that in 1 second, then it's going through all those steps to get 1 wow.
See, if we were to combine these two waves, if we were to add these two waves, we would get a bigger wave here, right? What's going on right here? Nothing, right? So we would have a wow, and then a down, and then a back up to a wow again, all right? It's going to be a lot of up and downs in between. I'm just doing the overall. So when we're in phase, we've got a lot of energy. When we get out of phase, we don't have any energy left. It's silence. So you're going to get a wow, wow going on.
But there, in between the 1 and 2, it looks like it's the same, so let it go down.
Right here?
No, between the 1 and 2.
Well, yes. So if I were to actually graph this, which you guys did in your lab, you would have it, it would actually look like something like that.
You could have done that assignment.
But then, would it still make that red sound?
The overall energy, what's the overall energy?
Wow.
Yeah, the overall energy
What do
is
you mean
big.
the overall energy, bro? What?
What's the overall energy right here in the middle?
0.
0. What's the overall energy here at the beginning?
Big.
It's big, right? What's the overall energy here? So when you are listening to it, you're going to hear, wow, wow. All right?
What is this?
You guys are not wowed by the wow. So when you have
I
new
think we're
notes
wowed
that are
and
out of
understood.
tune, they're going to be doing this wow, wow, wow. When they get closer and closer to the same energy, they're going to have fewer and fewer of these because they're closer and closer and have less happening per second. So the fewer you have, the more you're in tune. The more you have, the more you're out of tune. Just think of it, if you're walking with a little 3-year-old, you know, they're taking a lot of steps for every step that you're taking, right? And it won't take very long before you are back in phase. Every couple of steps, back in phase. But when you're walking with your boyfriend or girlfriend, your steps are close to the same size, right? You'll have to walk a lot further before you get back in phase again. Okay.
I got it.
How many got it? How many kind of get it?
Kind of.
How many still say, Mr. Singer, you're making this up?
I don't understand why this relates to this, though.
Relates to what? You can put your thumbs down, thank you. What?
I don't understand how that relates to that. Is that...
How what relates to what? This to that?
Yes.
Because if I play the strings and they're not putting out the same frequency, they're going to constructively and destructively interfere. So they'll get louder and quieter in a regular pattern, and that's the beats. Hear the beats? No? You hear the beats?
Yeah. I don't know.
You don't know? No.
Oh, yeah.
You hear it?
Yeah.
Okay. That's because they're just slightly out of phase. And then when they're in phase, they don't have the wow wow because they're completely constructively interfering.
So it's just.
It's just, yeah, wah. There's no wah wah, it's wah. Okay?
What?
All right. That's one concept, and that's a test question, Sydney. I know you want to know those
But
things.
I understand that,
So,
and I understand the
If,
guitar.
if the frequency is 400, and there are 3 beats, what's the frequency of the other string?
397 or 403.
That's right.
No.
understand.
What is the frequency
Oh,
of
because
the
it's
other
either
four?
3 up or 3 down.
Right.
Like the,
Right.
So it's not a.
Wait, so if the frequency is 400 and there are 3
The
beats,
strings.
what is the frequency of the other string?
Yeah.
yeah.
So
But like, won't it
It's
eventually
either
like
3 plus or
end?
3 less. So it's
like just
either
taking a section.
397
Just taking a section out.
or 403.
And how do we know if it's up or down?
So,
Well, you can't tell by just knowing the beats. As you get used to listening with your ear, you'll be able to tell.
But how would we,
But what about when
out
it's
of this
stopped?
question, how would you know if it's 3 up or 3 down?
You don't. That's what I just said to him.
both.
So if you
Your
kept
ear
playing
can
this tune
tell,
over and over
but,
and over, it looks
Otherwise, there's no way to know.
So just put
But
both
because
in?
it's ending,
Right.
the
so
red
if
line's
the
closed. and
frequency,
it
for
just goes
example,
back.
is 400 and you ask for 5,
Yeah.
then it's either 5 up or 5 down. So depending on the numbers that you ask, that would be the range that you have on that.
Number 3
Exactly.
is where the 2 strings
Right.
came into
Okay.
sync for a second.
Now we've taken care of
How
beats.
does it?
You just one of them was slower. So one of
The
those
next
three-
thing I want to touch bases
one of those
on
is section two.
is actually, I kind of skipped over it. I forgot to tell you about
So you
the
try to
Doppler
make
effect.
simple sound.
Um,
we do this one?
We were trying to match each other's
Did we talk about
frequencies.
Doppler effect? I know you did it in your homework, but I think I forgot to teach it to you. Is that right?
But when I like, when sound emits, kind of like,
So the Doppler effect is the
And that's what that.
effect that you think of as like a racetrack, or maybe on the side of the freeway you hear meow.
yeah.
Okay. Now, it's hard for our brains to separate sometimes pitch and intensity. Pitch and intensity. Pitch is the frequency. Intensity is how loud the sound is. As a car is coming towards us, it gets louder. And as it leaves us, it's getting quieter. But it's also true that the pitch will change. So here's what we want to think about. If we have a car, that's not working.
I like your car, Mr. Singer.
Yeah? This car is just flying, all right? And they blow the horn. The horn is blowing, and it puts out a sound. Now, every sound wave it's creating, is the car sitting still? No. So as it makes a wave, it starts going in the same direction as the wave. So what happens to the distance between these waves?
Really
Really
close.
small.
They're closer together, right? Well, what about going backwards?
They're farther apart.
They'll be farther apart, so the waves are, I'm exaggerating here, are further apart. Think about it, let's say you're in the swimming pool, and you take one of those kickboards, and you start making waves in the water. You're standing in the water, and you start making waves. But instead of standing still, you start walking. What's going to be true about the waves between each other as you walk? Are they going to get close together?
Yeah.
Yeah. When we change the wavelength, what have we done? We've changed the frequency, which therefore changes the pitch. So what's the pitch going to be like on the front of this car
Higher.
compared to the back of the car? Lower. So we get this sound of meow. All right, that sound goes from higher to lower. Why? Because it's getting squished and then it's getting stretched. Now, the person in the car, what pitch do they hear compared to the person in front of the car?
They hear a lower pitch.
Lower
than the
pitch.
person in front.
What pitch do they hear compared to the person behind the car?
Higher pitch.
Higher pitch. So all 3 positions are going to hear different pitches from the same source. So this has implications on all kinds of things, but one of the interesting ones is that light is a wave, right? So, I'm gonna fix this. um, so light is a wave. Now it goes super fast. Yeah, just keep running the video. Then they can
Oh,
see it later. And, just want to make sure that as I move around you.
Oh, I got you.
As light is super fast, so it's really hard to tell if we're going to get the Doppler effect with light. But what if the speed that something is moving is actually in the order of light? Could we see a shift in what color light is, depending on how it's emitted?
Yes.
Yeah.
The answer is yes. Now, I'm told, I have not studied this myself, I don't have the tools, but you can look it up. Every object in the universe is what's called red shifted, which means the wavelength of the light is heading towards the red direction. So as you look at a rainbow, what are the colors? The first one is red, orange, and so as we go towards red is shorter wavelength, a longer wavelength. So if the wavelength is getting longer, what does that tell you about the object you're looking at?
It's moving.
Is it going towards you or away from you?
Away from me.
Away from you. So as they look everywhere in the universe, and they look at the line emission spectrum from like hydrogen, we know what colors those are, right? And you know what frequency, you guys calculated them last year. You know what frequency it should be, but then you point it at this star and you get a different frequency and you know it's hydrogen. You say, wait a minute, that's hydrogen, but it's not the correct wavelength, it's a little bit longer. So what do you know about that star? It's going away from you. Every object in the universe, they say, is redshifted. So what does that mean? It's moving away. And this is one of the supports for the evolutionary theory of the Big Bang theory, because if we're exploding, no matter where you are in an explosion, every particle is moving away from all other particles, if you think about it. So if you're not in the center of it, but you're blown out, and let's say you're right here, you're still moving away from these particles faster away, right? So you're still going away from this particle, even though it's going this way, you're going away faster. And the particles that are past you are going away even faster yet. So you're going away from everything. And so that is a little support for a Big Bang. The problem with the Big Bang is that no one has an idea of how you get a bang in the first place.
God can speak the Big Bang.
God could speak and it could bang. Or perhaps we don't have enough understanding of what's going on to really interpret our data correctly.
Couldn't it happen that, just back into theory, that there was something before and then it just collapsed and then went back?
Yeah, but
Like,
it could be, but then what was the something before, so, and we don't know. We don't have an answer for that, yeah.
Do you think when God said let there be light that it was the Big Bang?
could be.
I'm going to say, to start with, I don't know.
I think it was.
I think that when God said let there light, there was some pretty big banging going on. But there's also the likelihood that there were things in existence before the world was created. How much of the universe was created before? I don't know. How long was the earth here before God actually made it habitable, before he created the living things on it and so forth? Because the Bible just starts out saying the earth was what? Formless. And without, yeah, which would almost suggest that it's possible it was here all along, or for a long time, before God said, okay, now I'm going to work on this planet. The Bible doesn't say. It does tell us that in 6 days he created all the living things, but it doesn't tell us when the rocks were made. Don't know. Don't know. I think that someday we may find something of an answer. But until then, but it is something you should know, as whether you're evolutionist or creationist, you should understand that the Doppler effect is observed by telescopes for other objects in the universe. Okay, last concept is back to page 422. What? 1002. All right, so going back to here, remember we talked about strings, and when we play a string, let's say that this is 1 meter, which it's not, but let's say it's 1 meter. What is the wavelength of that sound? This from here to here is 1 meter.
Half a meter.
The other way,
2 meters.
2 meters, because this is just half of the wavelength. The other half is
Yeah.
out here, okay? So when you play the fundamental, you're only getting this and which is how much of the entire wave? Half of the entire wave. So when we want to figure out the frequency of a string, how do we figure it out? Well, n represents the harmonic, and if it's this one, it is a 1. Why? That's the fundamental, okay? So we just, you can almost ignore it, but that's a 1. What if I wanted to know the next one? Well, I put a 2 there, and so on, right? V stands for the V, or the speed of the wave in that medium. In the case of a string, we'd have to calculate that. Yesterday in the lab, you started out with, what was the speed that we put there? From what? The speed of sound in air. So whatever that speed is, that goes here. And then why do we have the 2L? Because from here to here is L, and we need to do what to that length?
Double it.
Let's double it so that that's the actual length. If we do that calculation, we will know the frequency. Or we could go the other way and say, if I know the frequency, I could actually calculate how long my string is. That's how we did strings. Now, what about twos? This is what you started to play with yesterday. The weird thing about twos, what do you notice the difference between the antinodes and nodes in a tube compared to a string?
Antinode is in the middle, not the ends.
Well, say that again.
Like the nodes are in the middle and the end.
So the node is sort of in the middle, but more importantly, yes.
The two outside ones, you're never inside the two, you're outside.
Yeah. So the antinode is actually at the end. Whereas the string, the nodes are at the end. Okay? Now, I'm drawing the fundamental here. Could we have harmonics of that fundamental? So we could have more and more waves in here. We could actually have, let me try, I'm going to try. So you see how we've got antinodes here? Another antinode here, but the antinodes have to be at the end. So this will be the second harmonic of that, that pipe. So how do we figure that out? Well, the math turns out to be the same, because how much of the wave is in the pipe?
2 times, or half of it.
Half of it, right? Here's another quarter, and here's another quarter. 2 quarters make a half, and so there's half. So you notice the equation turns out to be the same. It's the same as this one. And that's easy. But then this is the one that messes us up. This one here. When the tube is closed at one end, then we have to have a node at this end, and the open end has to be antinode. So now how much of the wave do we have inside the tube?
Like 1/4.
A fourth. Which means how much is outside the tube?
3/4.
3/4. So if this is L,
Then we have to do
how do we do this equation, do you think?
4 instead of 2.
So we're going to put N here, and we're going to put V here, and then what? 4L. So now, hopefully you understand the equation, so then when you use it, you understand why I'm going to use what I'm going to use when I use it. Yeah.
For example, I was doing page 425, and one of the questions I said is there was a harmonic B or B flat or something. How do we know like the number, the harmonic
The
number?
letter, like B or whatever?
Yeah, how do we know like the harmonic number of B flat or C something?
Well, we have named all these notes, and music theory is really cool, and I'd love to learn it all someday. But we have chosen to name certain frequencies, like a C. I think it's 440.
yeah,
No, an A is 440. We've named that frequency. Now, if I wanted to find the harmonic of a 440, if the C is 440, what would be a harmonic of it? You would multiply it by 2. You get, so this N is representing the harmonic. So if it's 1, it's all of this times 1. So the second harmonic would be all of this times 2. So if my fundamental is 440, what's my next harmonic? 880.
Oh, okay.
Which is double. Or if it's not the harmonic, maybe it's the third or fourth, then we would just divide it to get to the fundamental. Make sense?
Yep.
All right. So that is it. Just watch out for this tube, and you have to listen. Is it closed at one end? Why can't it be closed at both ends?
Because then where?
Yeah, the air can't move around with that. So organs and all kinds of instruments. Let's see, you play the clarinet?
Nope.
Wrong. Which one? Trumpet. Trumpet. So is the trumpet a tube?
Yes.
It's just wrapped around in circles, but could that thing be a straight line? Sure. It's a tube. Now it gets a little bit more fun because is that tube the same size and no, it's and so how do we change the length of the tube? The trumpet is not made out of just one tube. It's made out of a bunch of tubes. Now what if the trumpet did not have any
Valves.
valves? Thank you.
It'd be auto.
Do you know why these things like you hear the bells do?
Because it's going out of
Because you can only play the harmonics of the tube. If you don't change the length of the tube, you can only play the harmonics, the fundamental and all the ones above it. And so, like a bugle, which has no valves, it's just you can only play the harmonics.
Have you seen a true?
So, if you want to play other notes, what do you have to do? You have to change the tube. And so you can change the valves to change the tube. And so now with the trumpet with valves, you can change all those things. How does the trombone do it?
You change the length. It changed the slide.
You just slide it and you change it. So all the instruments are all doing, what are they doing?
Changing.
They're changing the length of the tube.
That's so
cool.
interesting.
Yeah. All right. That's all I got. We have about 5 more minutes.
Can I
Let's
use the
stop
bathroom?
the-
Is she-
For a second.